Yeah, thanks for the invitation to the talk and also for the invitation to show some of our work in the bodybuilding exhibition. So as said, I'm working at the Institute for Computational Design. There I'm working with a really great group of colleagues. The institute is led by Professor Achim Menges. The focus of our institute is computation in materialization. But most importantly, not a subsequent step of these two, so not a design process and a subsequent step of making and producing, but we want to look into computational design methods. We're looking into computational design strategies that allow us to integrate the fabrication of structures from the very beginning into the design process. So there's a certain legacy historic precedent of that in Stuttgart. Most of you know Frei Otto. The interesting thing here is, for example, how the relation between such a cable net and a soap film bubble. So that's the general approach that we focus very much in our design strategies, that form is emerging through a set of boundary conditions and is not drawn by the designer and later on implemented with various methods that might or might not be suitable to achieve that specific form. So this shape is not drawn, but it really emerges through a set of material properties. So that's very different how architecture is often constructed. Often you have a serial production, industrial production of identical parts, which are then added together, and that's quite different from how structures and form are developed in natural structures. So through natural morphogenesis, so the development of form and growth of material in response to its external and internal stimuli, allows such a structural system, for example, to be very locally differentiated and respond to its local requirements, which in the end allows a lot of material savings and also a very interesting degree of functional integration into these structures. So we're looking into a way how those properties can be transferred into architectural structures. And the interesting thing is here how computational design strategies are suitable to go from this natural morphogenesis towards a computational morphogenesis of form that integrates fabrication aspects from the very beginning. There's a small distinction that is important to make. So we're not just merely automizing or computerization of tasks, but we use our computational design tools as explorative and generative methods to come up with novel solutions. That requires a very integrated design approach. So computation, simulation, and fabrication are simultaneously integrated into the design method. Furthermore, also computational design strategies are very suitable to be the point of confluence within a multidisciplinary undertaking. So working together with biologists, engineers, material scientists, a computational design tool allows you to integrate a lot of these inputs from adjacent disciplines into the design process. We work on a one-to-one scale, so we often test the design and fabrication strategies that we develop in a full-scale prototype. So here you see some of our research pavilions. Pavilions are an interesting method of testing this research because on the one hand it's a full scale, so you see if the detail, the connection and the scaling of the structural principle work out. On the other hand, you can leave away a lot of requirements you usually have for architecture that allows you to focus and foreground a specific research interest. Often we start our investigations with natural structures. What you here see is a pincher claw of a lobster. And there's one thing that we're interested in is how this complex form emerges to meet the structural requirements. But the second layer that we're interested in is a specific material layup. So nature often uses fiber composite materials, which uses the anisotropic character of this fibrous to differentiate its structural behavior. You can use the same material of fibers and arrange it in various ways, and for example in the lobster generate very soft parts of the skin and very rigid parts just by changing the material organization. And furthermore, what I mentioned before, functional integration. So this is not only a very material efficient structure, but it also negotiates the internal and external climate, gas exchange, liquid transportation, and so forth. That's a general principle in nature. So wood is similarly built. So tension and compression wood has different fiber orientations. Or even within our bodies, for example, collagen fibers are used. And depending on how you arrange them, you either get a soft connective tissue or a tendon, which has very different material properties. But it's the same material, just organized in a different way. So what does that mean for the architectural design process? That means once we can reach down to the level of the material with our design process, we can have what we call like a designed materiality. So during aligning the fibers in the structure, the material layup is already defining the structural system that we can generate. So the question is how these structural principles and that potential that we see in natural structures can be transferred into technical applications. For that, we use materials that are already used since quite a while in high-performance applications like aerospace, for example. We have fibers like glass fiber or carbon fiber that are embedded in a polymer matrix. The question is how these can be transferred in the architectural construction industry, because the methods used in other industries so far use the material that is actually quite formable and therefore very suitable to implement these biological geometries that we saw before, these performative morphologies. But in industry so far, a costly formwork is required, which means you have high cost to produce the one mold, and therefore it bounds the formable material back again into a serial production logic. So for architecture, where we often have unique pieces, and especially when we want to take this differentiated structure from natural inspirations to have more material saving and locally adapted structures, we have unique parts. So we need to come up with novel fabrication strategies to enable the usage of these materials in architecture. So I'm going to show a row of projects that I've been working on at the Institute. So for this project, we collaborated with a row of various institutes. Most important is the Institute for Structural Design with Professor Knippers, who are doing all the simulations for the structural behavior of these prototypes. And we have industry support and work together with our master students on these projects. What we did here is, what you see here is a fabrication technology that we developed, which is robotic filament winding. And what is important is that it's a coreless winding technique. So the steel frames you see are reconfigurable, so they can adjust to various building component geometries. And the fiber layout can be individually programmed by programming the robot movements. What you see is that there's no mold between the two frames, which means the geometry of this part is the curvature that you see in this piece, for example, is emerging through the interaction of the fibers pressing onto each other, which you can fine-tune through the order how you apply these fibers. That means that we don't need to produce a costly formwork for this piece, but can really produce one-off components with the same fabrication setup. The biological role model here for this investigation were beetle shells that we scanned in collaboration with scientists from Karlsruhe Institute of Technology. And very important when you look into these biological structures is you see incredible complex structure, and you always need to have a comparative study of various role models to see what is actually the underlying functional principle that needs to be abstracted and can then be transferred into architectural applications. It doesn't make much sense to just reproduce what you see here. So what we were interested again were when we had a closer look in electron microscopy scans is on the one hand the geometry. So how are the elements shaped to be really suitable for this load transfer, and how is the material, how are the fibers arranged in these beetle wings? And then I mentioned before the natural process of morphogenesis. What we made, we took all these principles and integrated them into an algorithm to come up with a computational morphogenesis. So here again, the form is not designed and drawn by a designer. We rather define boundary conditions, and the form is emerging to negotiate multiple parameters. For example, the fabricatability on the robotic setup, which has certain constraints to the size of the element, the material behavior is integrated, and the structural capacity is adjusting the individual elements. So once we have this global morphology of our components, there's another algorithm defining the order in which the fibers need to be applied to the system. So what that allowed us is to fabricate individualized building components, which each have an individual geometry and a unique fiber layout to have the most material efficient structure in the end. What sounds more like a technical task is in the end also very interesting from the perspective of a designer and an architect, because the material characteristic is very much articulated here. So composites are already used, as I said before, in other industries, but often you just see slick surfaces and you don't know if there's a metal or a composite underneath. Here the anisotropic characteristic of the fibers and the robotic filament winding process are really visible and articulated in the architectural design outcome in the end. So the approach is quite different to usual approach to architectural design. As I mentioned in the beginning, it's not the initial development of like design of form and then a subsequent step to find a method how that could be built, but we integrate the fabrication process, the material characteristic from the very beginning and generate forms that we know can be fabricated. And through the novelty of the applied mechanisms, we also achieve very interesting design features in the end. You see how the glass fiber is transferring the light and the whole thing starts glowing at night, for example. A follow-up project of that's also featured in the bodybuilding exhibition is a fair stand that was directly commissioned by the rector of the university, where we used a similar filament winding strategy to build this carbon fiber reinforced polymer components. Here, the requirements were a little bit different. It was more transportability, weight. We need to produce them quite quick. So that allowed us to not go in a very experimental way, but to refine structures that we had developed before. So here you see that components are stackable. We increased the accuracy quite a bit, and we were able to increase the winding speed by a factor of 20, so we can produce these things super fast now. And those are really important steps to also bring it closer to application in building industries, these refinements that need to be made before it's actually feasible to apply these strategies. But again, that was not only a technical refinement, but again, we maintained this articulation of the material characteristic. You see the fiber alignment and interesting features like the shadows that come with it. This is a recent project that's currently shown in Stuttgart. It's again a very multidisciplinary undertaking with structural engineers. We had aerospace engineers involved, biologists, and machine engineers. So again, our master students from the iTech master program were involved in the construction of this. And we got the material sponsors and the machines. For example, we have a really strong cooperation with KUKA, who are always lending us the right equipment for the projects. Relating that to what I showed before, where we were looking into a final morphology of an outcome in biology, where we were transferring geometric features and material organization features into a very efficient lightweight structure. The approach was quite different at this project, where we were looking more into a behavioral model. So we were more looking not into the final result, but into the process, how are fiber structures generated in nature. And one very interesting model that we found in collaboration with the biologist is the water spider. So the water spider lives its entire life underwater and still needs an air bubble to breathe. The interesting thing is now how a very complex fiber arrangement is generated without the need, for example, of a costly, elaborate formwork, linking it back to constraints that are currently coming from industry and interesting solutions that we can find in nature, how these things are resolved in a very integrated way. So what we did, we got several of these spiders and had a setup in the basement where we were observing them, building their nest. And it was interesting to see how in very different environments, so we were changing the supports it could connect to, and applying some currents and seeing how robust the structure was. every time the robust set of instructions, the behavior that the spider was following allowed it to build this rigid cocoon-like structure. So there's very interesting aspects also, again, on the level of the material. How is that hierarchically differentiated? How are fibers bundling, spreading out? Which parts are reinforced? Which are held a little bit loosely to have a little bit more give? And all these features we were interested in then need to go through a special evaluation. It's basically like a classical approach towards biomimetics, where we say, what are the features that we're interested in, because they address something that we currently have as an issue in technical applications, that those processes in nature need to be understood, and then it's very important that one can abstract them. So, and you will find that a lot of these things later are not transferable. There's only several things that you can really understand. You can figure out that even the underlying abstract principle is really still interesting for you as a technological application. And then most importantly, that it can be also implemented with the means that we have nowadays. And what we came up with is such kind of a setup that takes two aspects from the spider. The one is a very reduced formwork. So we had a numerically supported formwork here that compared to the formwork you would usually need in industrial applications is really very material efficient. It's just a very thin foil that's air supported and temporarily air supported. And the second aspect that we were interested in is what I mentioned before, is the behavior of the spider. So how does the spider determine where the next filament is to be laid? And that is, again, a very multidisciplinary undertaking where you need an integrated design approach, which is computationally supported. So there are fabrication constraints, structural constraints, and biological rules that need to be integrated into a design and fabrication system. For example, the robot has a certain reach that needs to be incorporated while generating the general shape of the prototype that we wanted to produce. In the second step, you see how is that structurally performing. And those are already two constraints that need to be negotiated. When you want to lay your fiber later, you need to know where should that fiber go to transport the forces that occur. On the other hand, the robot has certain constraints where it can reach better. So those things can be negotiated very nicely through a computational design system. For example, here we chose an agent-based approach where you can imagine that a point is running across the surface and defining its path. The trace it leaves is basically a fiber that we want to place later. And the agent has a certain behavior similar to the spider. The spider always takes decisions where it should put the next fiber. Similar does this agent-based model where we define a layered system of behaviors. And the interesting thing is that we can then weigh these. We can give a little bit more priority to the structural aspect or to the fabrication aspect and get a large variety of different outcomes of this behavioral design strategy. So in the end, it's not that the computer is taking the role of a designer, but it's actually giving us, resolving a lot of complex interrelations and gives us a lot of choices that we can then later follow. Interesting architecturally here is also how it really differs from roof, wall, window topologies and has more gradients in structural distribution of the material. Here's the first test, how the robot is applying carbon fiber onto that ETFE film, and what you see is that it's deforming quite a lot. So it's not only a new approach from the computational design side that we're following in this project, but it also requires a different thinking for the robotic fabrication strategy. Because before, the robot was only executing a program that we gave him. A lot of information was integrated into that program, but then the robot was just executing. Now we have a very dynamic fabrication scenario, which means the robot needs to be live reacting to the deformation of this formwork, for example. Amongst others, there were the amount of glue and the amount of fibers that are extruded as dynamic parameters that needed to be calibrated during fabrication. So that's something that we call or is generally called a cyber-physical fabrication system, where there's a direct feedback between the physical and the digital. That also includes the build-up of a very specific tool. So the robot is a generic arm that can be used for a various amount of tasks unless we give it a specific purpose by designing our tool. That's also very important to mention in such an integrated design project, that by designing your tool as an architect, that becomes a very important part in the design process. So it defines the design space that you're able to explore. And here you see how the digital and the physical are really fused together. And while the robot is running, we have all the data, and the robot is live responding and reacting. Here you see how we inflate it, and then the robot was gluing the fibers from within the pneumatic formwork and creating this very dense fiber composite shell. Again, what is important is that this is not only a very interesting lightweight construction, so the construction weight of this is only 250 kilogram, and it's close to 50 square meter big, but it also has a lot of architectural qualities that can be explored. So it's not only a performative investigation of technology, but it's also about exploring material characteristic and see how that can be employed as a designer. Thank you.